Good afternoon, everyone. So today we'll start with the series of lecture on hyperspectral. The first one would be an overview on hyperspectral remote sensing, which is just going to touch you about the physical basis of hyperspectral data collection, the sensors available in hyperspectral data collection, and issues related to hyperspectral data processing. And in depth, these topics would be then covered later on subsequently in different lectures. So as hyperspectral remote sensing is generally known as imaging spectroscopy, is a relatively new terminology, you can say, in comparison to multispectral remote sensing, which is used for detection and identification of minerals, terrestrial vegetation, and man-made materials and background. This has been, in fact, imaging spectroscopy has been used in the laboratory by the physicists and chemists for over 100 years. As such, it has been used, these instruments has been used in the laboratory for identification of materials and knowing their composition. Spectroscopy can be used to detect individual absorption features due to its specific chemical bonds in liquid, solid, or a gas. And the concept of hyperspectral remote sensing came way back somewhere around in mid-80s, and it was, at this point, it was widely used by geologists for mapping of minerals, and the actual detection of the material or the minerals dependent on the spectral coverage, the spectral resolution, and the signal to noise ratio of the spectrometers, and the material and the abundance of the material and the strength of the absorption features for that material in the wavelength region being measured. Now, as it says, higher spectral resolution leads to much more definitive information on the composition and the certain physical properties of different materials. So in early 80s, Dr. Alexander Goetz and his colleagues at the JPL laboratory in the US, they developed this concept of the hyperspectral remote sensing, a new instrument called Advanced Visible Infrared Imaging Spectrometer. This instrument carried a detector which had capability of measuring in the extended spectral regions. To extend, this was an instrument which was an extended version of the ground-based imaging the ground-based radiometer spectrometers, and they were mounted on the aircraft on moving platforms. And the distinct value of obtaining hyperspectral curves was, it made it possible, the observations collected by the instrument kept on these aircrafts made it possible to acquire detailed information about the material and classes present on the Earth's surface. Essentially, the curves which you see are a continuous spectral plots that measure the reflectance from the ground features in the spectral regions, wavelength regions, responding to the solar illumination. Now, hyperspectral remote sensing combines both imaging and spectroscopy into a single system, which often in a single system, whereby it incorporates large data sets and requires new processing methods. It generally is composed of bands which is in the order of 100 to 200 spectral bands of relatively narrow bandwidths, maybe from 5 to 10 nanometers. So you can say hyperspectral remote sensing is a science of acquiring digital imagery of the Earth's material in many narrow contiguous spectral bands. Now, there are various versions of hyperspectral remote sensing. We can say there are different nomenclatures being given as hyperspectral spectroscopy, imaging spectroscopy, or narrowband spectroscopy. And although they have different meaning in the sense of a direct translation, but spectrometry means measuring, spectroscopy means seeing, hyperspectral means too many bands. So the acquisition of bands, and the underlining word is the acquisition of images of hundreds of registered contiguous spectral bands, such that for each picture element of an image it is possible to derive a complete reflectance spectrum. Now we'll go, as you all know, when the light interacts with any object on the ground, light of certain wavelength is preferentially absorbed, while at other wavelengths it is transmitted in the substance. Reflectance, as you all know, is a ratio of the intensity of light reflected from a sample to the intensity of the light incident on it, measured by reflectance spectrophotometers, which consist of a light source and a prism to separate light into different wavelengths. Now this light beam interacts with the sample, and the intensity of reflected light at various wavelengths is measured by a detector relatively to a reference standard of known reflectance. Thus you get a continuous reflectance spectrum of the sample is measured. Now reflectance spectra have been used for many years to obtain the compositional information of the Earth's surface. So as you know, we measure the reflected and the emitted radiations. So the photons strike the Earth's surface, and certain wavelengths are absorbed and certain are reflected. So various material absorb sunlight over specific wavelength intervals, resulting in absorption features in reflectance spectra. So this is what is important in hyperspectral remote sensing, that is the absorption spectra, which is a significant, or we can say a diagnostic characteristic of identification of a certain object on the ground. So the location and the shape of these absorption features provide information on the chemical composition of the materials. Now if you look, the reflectance, the several classes of sensors are available, and if we plot as a triangle in which the corner members are determined by the principal parameter being measured, because in remote sensing the three main characteristics which we measure are your intensity, spatial information, and the spectral information. The intensity, you can say, is related to the radiometry value. So if you measure only the spectral information without the spatial as well as the radiometry, you have spectrometers. If you measure the spatial information, they are images, the photographs like a camera which measures the spatial information, and the intensity information, which is measurement of the energy reflected in a predefined wavelength, they are the radiometers. And if we combine the radiometer and the spectral information, we have spectroradiometers. The spectral information combined to the spatial information, you have the imaging spectrometer, which is your hyperspectral remote sensing instruments. If we combine the spatial with the radiometer, radiometers, as I said, is in a predefined wavelength, or what we call it as a broadband wavelength, is the imaging radiometer. And the combination of spectral and radiometers are the spectroradiometers. Basically, these are the ground measuring instruments. Now, the spectral sensing can be divided into the various regions. You have your broadband remote sensing. Before this, we have a panchromatic data, which is having measurement only in single wavelength. Then you have a broadband remote sensing, where we measure the visible, which is your panchromatic and the short wave. Then multispectral, which is of the order of the bandwidth of 100 nanometers, where you have a couple of bands, few bands. Example, in Landsat you have 7 bands, Iris you have 3 bands. Then hyperspectral, where the bandwidth is of the order of 5 to 10 nanometers, and you have hundreds of bands available. Then slowly we have the ultraspectral remote sensing, where still the bandwidth is less than 5 nanometers, and you will have bands availability of around thousands of bands would be available. Now, the advantage, as I mentioned, for hyperspectral remote sensing is, if you measure you have large volume of data, information available at one point of the feature on the earth, and you can generate a complete spectrum, the reflectance spectrum, a continuous reflectance spectrum for that particular feature on the earth, which can be used to interpret and identify that feature on ground. So what you have is, for each single pixel, you have three-dimension data, the X and the Y, which is the spatial location, and the Z, which provides you the spectral information which leads to a continuous spectral profile, or the reflectance spectrum, which enables you to identify the different land cover feature on the Earth's surface. So this is an example that with the hyperspectral remote sensing data, you can create the complete spectrum for each of the land cover, for example here for vegetation, water and soil. So if we compare the multispectral versus hyperspectral, we can say that the multispectral has separated spectral bands with gaps in between, whereas hyperspectral data sets, there are no spectral gap, they are contiguous in nature. The multispectral remote sensing is a broadband remote sensing where you have larger bandwidths, like 100 nanometers, whereas hyperspectral remote sensing are narrowband remote sensing with a bandwidth of the order of 5 to 10 or 10 to 20 nanometers. The multispectral remote sensing is a coarser representation. It provides you coarser representation of the spectral signature, whereas hyperspectral remote sensing provides you with a complete representation or a continuous representation of the spectral signature. We can have an example here. This is the spectral reflectance pattern for various land cover features on the earth, like vegetation, sandstone, limestone. Now if we look at the same these features with different types of remote sensing data, with a broadband, moderate spectral resolution, and with a hyperspectral resolution, or with a narrowband remote sensing, you can see that with Landsat, which is a broadband remote sensing data, the spectral signature is not complete. It's a very brief sketch of the spectral profile. With MODIS, it is slightly improvised with the number of bands increasing, whereas with hyperspectral, you are getting a continuous spectral profile which can be utilized for identification of that particular object on ground. So each and every, the values at, if you look at here, there is an absorption at 1.4, around 1.4, there is a peculiar absorption in the reflectance pattern, which is not visible in the other two, and this is a unique characteristic of this particular feature on ground to enable us to identify that feature. So it's a distinguishing characteristic, that particular feature, which is missed out in the broadband remote sensing. So you can say this is the fingerprint, which is not seen with the broadband remote sensing data like Landsat and MODIS. So the molecular makeup of a material results in patterns of reflectance and absorption across the wavelengths that become a unique identification characteristics, or you can say fingerprint of that material. Therefore, by looking at the spectrum from a spectral image, if we have this continuous profile of the reflectance pattern, we often can identify the material existing inside that particular area or pixel. And multispectral sensors measure multiple wide separated wavelength bands, whereas hyperspectral they measure in narrow contiguous bands. So although most hyperspectral sensors measure hundreds of wavelength bands, and most multispectral measures few, it's not the number that matters. It's not that if I have 100 bands that defines and say it's a hyperspectral sensor. So the number of the measured bands is not the criteria to define the difference between multispectral and hyperspectral. It is the narrowness and the contiguous nature of the measurements that makes it as a qualifier for hyperspectral remote sensing. So even though you may have large number of bands, but the data is having large wavelength gaps, and it's not contiguous in nature, and it is broadband, it would not be said as hyperspectral remote sensing. Only the wavelength regions, the spectral resolution should be narrow, and the data should be contiguous in nature. There should be no wavelength gaps in between. So for example, let's consider a sensor that measures only 20 bands could be considered as hyperspectral if the bands are narrow, that is, they have a spectral resolution of 10 nanometers, and if the sensor measured 20 wavelengths with 100 nanometer as the bandwidth, it is not qualified as, it cannot be called as hyperspectral data sets. It would be called still as a multispectral remote sensing data. Now this is another example of multispectral versus hyperspectral. These are the three reflectance characteristics of three land cover features. The green is the vegetation, the red is the silty loam, and the white is a talc. It's a mineral talc. They are three distinct shapes, but with relative detail. If you look, the profiles with the multispectral are more or less straight lines which are there, which is but with hyperspectral data, this is an example of airborne visible imaging radio infrared imaging spectrometer, which views the same regions with much more detailed information than a multispectral remote sensor which you saw. So the gaps in these spectra which you are seeing are due to the atmospheric absorption, at which the atmosphere absorbs the radiation and no signal is received in these regions. That's why we have this gap. Otherwise, if you look at the complete spectra, you can clearly make out that the vegetation spectra resembles that of the reflectance characteristics of vegetation, the silty loam, and the talc. So you have much more detailed information, whereas you have information also related to these absorption zones, which are the typical characteristics, as I say, fingerprints for identification of that mineral or object on ground, which are missed in the multispectral remote sensing data. So most of the Earth's surface material have these what we call as the diagnostic absorption features in the complete spectrum region from 400 nanometers to 2500 nanometer range of the electromagnetic spectrum, and these diagnostic absorption features are typically of a very narrow spectral appearance, and the surface material can be identified if the spectrum is sampled at sufficiently high spectral resolution, because these absorption zones are sometimes very, very narrow. If we measure in a broad band remote sensing, they are lost. So if they are sampled and measured at a very, very narrow spectral regions, then probably we'll be able to capture them, and which enables us to identify that particular object. For example, these are two minerals, kaolinite and elenite. If you look at it, they have an absorption zone between the wavelength region 2.1 to 2.3, and the absorptions have a different shape and position. So both the position and the of the blue, which is a kaolinite, and yellow is the elenite. If you look at the two minerals, this is a zoomed up version. So if you look, they have a very close regions where these absorptions occur, but their shape and size are different. And if you look, these both absorption zones are very near to 2.2 micrometers, but there is a small difference. The exact position and the shape, the position and size and shape are different. If you sample the spectral measurements at a very narrow, that is at 10 nanometers, probably we will be able to capture these absorption zones separately, and that would enable us to identify these two minerals separately. Otherwise, in a broadband remote sensing, this would be normalized, and what you will measure, you will not be able to see the distance between the two objects. Now we'll just go into a little bit on imaging spectroscope. I mean the fundamentals behind this differences in absorption. More in depth would be covered in the next lecture on imaging the spectroscopy by Dr. Sanjeevi. Now each land cover feature in terms of the vary in terms of the following properties: their chemical, physical, mechanical, reflective and emissive property. So these are the 5 parameters on which different land cover features vary from one another. Now the first 3 are more physical in terms, which is not measured by remote sensing. Instruments, ground-based instruments or in situ measurements are required to measure their chemical composition, physical composition and mechanical. What we measure using remote sensing is the reflective and emissive, and using these 2 reflective and emissive properties, we are able to diagnose or say something about the chemical, physical and mechanical properties. Now the reason for these absorption of these features is the interaction of electromagnetic radiation with atoms and molecules, which creates these absorption features in the spectra. Now the absorbed features are fundamentals. Overtones, they are the fundamental, they are due to the fundamental overtones and their combinations. There are 3 types of absorption processes: charge transfer process, electronic process and the vibrational process, which cause these absorptions, and they result at different wavelength regions. The charge transfer absorption process, they occur mostly in the visible region of the spectrum, and they are caused by light at certain wavelengths, causing electrons to be transferred between atoms. So when the electrons are moved from their energy levels, then it results in absorption. For example, from iron Fe3 plus to iron Fe2 plus, light at the proper wavelength causes an electron to be transferred from Fe2 to the Fe3 atom, causing the absorption. Excuse me. In general, this type of absorption is quite broad due to the charge transfer process. Hence, mostly it has been detected by broadband. It can be detected by broadband remote sensing or conventional multispectral remote sensing. This is the reason which causes the rusty appearance or the iron features, why they appear red. And this occurs mostly in the visible portion of the spectrum. In general, absorption bands caused by charge transfer are diagnostic of the mineralogy. Now, the reflectance spectra of iron oxides have such strong absorption bands that the shape changes significantly with the grain size. As I said, they are broad, these are broad in nature. These absorptions are broad. As you can see, wherever the T sign is there, they are the absorption zones, which you can see are quite broad in nature and can be captured by the multispectral remote sensing. The electronic transition absorptions. In atoms with an incomplete electron shell, light at the proper wavelength can bump electrons into different positions in the cell. And the isolated atoms and ions, they have discrete energy states. Absorption of photons of a specific wavelength cause a change from one energy state to a higher one, and emission of a photon occurs as a result of a change in energy state to a lower. And these absorptions are very, very narrow than the charge transfer absorptions, and the wavelengths of the absorptions are controlled not only by the type of atom but also the position and variety of its neighbors. The most common electronic process revealed in the spectra of minerals is due to the unfilled electron shells of transition elements like nickel, chromium, cobalt, iron, and the iron is the most common transition element in the minerals. And this feature or absorption due to the electronic process is especially useful in geological feature identification. Since subtle variations in the position of the band center are very important, it is necessary to have many narrowly spaced bands to take full advantage of this feature. Now the third one is due to the vibrational process. The bonds in a molecule or crystal lattice are like springs and with attached weights. The whole system can vibrate, and the frequency of vibration depends on the strength of each spring, that is the bond in a molecule, and their masses. For a molecule with n atoms, there are 3n by 6 normal modes of vibration called fundamental, and each vibration can also occur at roughly multiples of the original fundamental frequency. And this fundamental mode and the combinations with the overtones, they result in these absorption features. Okay. And these absorptions are also narrow in nature and can be detected with a spectral resolution of 10 to 20 nanometers. And they are specifically lying in the shortwave infrared region. So absorption due to the vibration process generally occur in the shortwave infrared regions of your electromagnetic spectrum. Like due to the charge transfer, they are more prominent in the visible portion. Due to the vibrational and the electronic process, they are more in the middle and the infrared and the shortwave infrared process. So many of the absorptions seen in the region from 0.4 to 2.5 micrometer region actually originate at longer wavelengths, and what we see are the combination and overtones of the original wavelength. So most of these absorptions can be detected with hyperspectral sensors. So these are few examples which are there, which are showing you different forms of absorption spectra. So this is a zoomed up version of the absorption feature. This is due to the charge transfer. This is due to the OH chemical bond, which is due to the electronic transition process. The absorption features which are narrower than the charge transfer process. Now silicates, they have different structures. This is an example where the positions of the silicon oxygen bond, they are stretching through the troughs and peaks, occur at different positions for different silicate materials. So the more the composition changes, the absorption zones also, they lie at different areas. This is an example of spectra of non-silicates in the middle infrared and the thermal infrared. They show different patterns of absorption due to the presence of silicates in different amount. This is an example for the vegetation features. For the fir and the pine, the absorption as the example of the calanites, they are very close to each other, which can only be detected with narrow band remote sensing, and it would enable us to identify the two land cover features, pine and fir. Now, if we look back, which are the wavelength regions which are important for identification of different types of features of the Earth's surface. For example, the wavelength range from 0.4 to 1.5 micrometers is useful for iron-bearing minerals, carbonates, and having various combinations of carbonates and sulfates. Between 1.5 to 1.85 and 2 micrometers to 2.5, it's carbonates and hydroxyl groups of carbonates, clay, etc. For vegetation features, the wavelength regions which are important specifically in terms of chlorophyll, pigmentation identification, plant water content, cellulose, protein, starch, nutrient, stress, nitrogen, cellulose, they are from 0.4 to 0.65 where these absorption zones might occur, 0.9 to 1.4, 1.4 to 1.9 and 2 to 2.4 micrometers. For snow and ice studies, to determine the snow grain size, snow depth, contaminants, liquid water content, it is the wavelength region is from 0.4 to 0.8 and 0.8 to 1.4 micrometers. So the requirement of spectral resolution is determined by the width of the occurring absorption. If the absorption is narrow, we would require high spectral resolution or narrow the bandwidth. So for soils and geological investigation, mostly in the near and shortwave infrared, spectral resolution of 10 nanometers, sorry, it's wrongly written in that, it's not micrometers, 10 nanometer resolution is necessary. And the bands which are required is from 0.4 to 2.5 micrometers. So for vegetation, water and iron mineral studies, it's 10 to 20 nanometers, in the region 45 nanometers to 670. For vegetation, clear vegetation application, it's in the red infrared region with 5 to 10 nanometers. Then again from infrared region it is 5 to 10 nanometers for vegetation and atmospheric studies, from 780 nanometers for vegetation and iron minerals. And again in the middle infrared region also it is for 5 to 10 nanometers. For soils and rock, for soil moisture related studies, the spectral resolution required is less than 50 nanometers. But in general, if you look for all various applications, the optimum resolution which is required for the various vegetation, soil and geological feature comes out to be 10 nanometers across 0.4 to 2.5 micrometers. So this is the optimum spectral resolution which is required to detect most of the land cover features on the Earth's surface. So we can conclude that the multispectral instruments can discriminate materials because they measure the different characteristics in the relative general sense, whereas hyperspectral imaging is required to actually identify materials on ground. So the most significant advantage of multispectral over hyperspectral is its greater accessibility due to, the one advantage you have of multispectral is that you have greater accessibility due to larger number of space-based multispectral sensors which are available. To date, you do not have many hyperspectral sensors, space-bound hyperspectral sensors which can provide you freely available data in contrast to multispectral data sets. So hyperspectral data sets currently also mostly are airborne. So the limitations of hyperspectral data, one we can say, is availability of the data sets from spacebound platforms. Since we are collecting large amount of data, they are sensitive to noise. It's difficult to interpret the spectral signature of an impure pixel, because impure pixel means it consists of many land cover features within one small pixel on ground. So the reflectance spectrum would be a combination of the features present within that pixel. So it's very difficult to identify or interpret that spectral signature of an impure pixel in case of hyperspectral. Then the need for calibration, because the high degree of need for calibration with hyperspectral data, because of the high spectral resolution of hyperspectral imaging, you have fine atmospheric absorption features may be detected which may be confused with ground material being imaged. So you need to calibrate them to remove those zones which are caused due to the absorption of the atmospheric particles, and then remove those before going for further analysis. So this is an example of mixed pixel where the small area, the pixel may have the presence of small or sub-pixel targets. So the spectral profile would be a combination of these two. The presence of boundaries of discrete parcels, you have two major land cover and the boundaries. So again, this would have a mixed profile. The gradual transition between land cover classes, there are two various land cover classes present here, and the contribution of the areas outside the area represented by a pixel. So the reflectance spectra of a mix is generally the weighted average of the spectral response present within it, and it will be difficult to interpret these features in terms or identify the object within those pixels using hyperspectral data. Another limitation of hyperspectral data is the data volume. The storage and transmission of hyperspectral data are one of the major issues where the volume of data is large. You have around more than 200 bands, and with higher radiometric resolution, the storage is one of the issues. then you have redundancy of data. There are overlap of information content over spectral bands. So not all data is needed to characterize a pixel properly. So there is an issue of data redundancy which is there with hyperspectral data sets. Now we come down to the data acquisition mechanism with hyperspectral and the sensors available with hyperspectral data. So hyperspectral data, you have different, similar to your multispectral, also acquires data in both whisk broom, push broom mode. So some of the satellites are measuring in whisk broom mode and the others with the push broom mode. For example, the Hyperion, they are with the push broom technology, whereas the AVRS and all with the whisk broom technology. So the major working principle is here, the energy reflected from the Earth's surface passes through the optics and it falls on the dispersing or the grating element, which splits the light into the different constituents or different regions of the electromagnetic radiation, and you have a detector which measures the light reflected in that corresponding to that particular wavelength. So here the major instrument which plays a significant role is this dispersing element or the grating element or the prism which is there, which splits the light into different electromagnetic regions, parts the spectrum, and the detectors which measure these radiations. Now, the development of terrestrial imaging spectroscopy started, as I said, in the late 70s by NASA's JPL laboratory and the Government of Canada private partnership, leading to an airborne imaging spectrometer in the US and the fluorescence line imager in Canada, with the first data being acquired in 83 and 84. And these activities subsequently led in 1987 to the first visible and near-infrared airborne imaging spectroradiometer, which measures the radiation in the visible and the shortwave infrared, which is known as the AVIRIS. And in 1988 to the first commercial instrument called ITRIS, which is a compact airborne imaging spectroradiometer. So many more airborne systems were developed since that time. The first successful launched civilian hyperspectral instrument was NASA's Hyperion on Earth observation satellite, experimental satellite 1, and it has been in orbit since 2000. Then a year later, the compact high-resolution imaging spectroradiometer on board ESA's project on board the autonomy proba platform, and then subsequently there were many. There was a launch by ISRO also, took an initiative which launched its visible near-infrared hyperspectral imager, which is called at HISI, on board the Indian mini satellite. And even Chinese also launched a satellite on the visible near-infrared imaging spectroradiometer, which is called as HJ-1A satellite in 2008. So these two satellites, which was launched by ISRO and Chinese, they both had core spatial resolution. So thereby there were opportunities to look into larger areas of sampling distance of more than, your spatial resolution more than 100 meters, combined with a larger swath and larger coverage spectral resolution. So we'll see these instruments one by one. The airborne visible infrared imaging spectroradiometer was designed and built, as I said, by NASA. It's a whisk broom type of scanner, and it flies on it's an airborne scanner, and it flies on various airborne platforms. The swath and the spatial resolution depends on the flying height. They could vary it and over ground speed of the aircraft. It covers an 11 kilometer swath at 20, in general it covers at 11 kilometer swath at 20 meter pixel size. The sensor measures the radiance levels at 12-bit radiometric resolution for in 224 spectral bands with 10 nanometer bandwidth, and the wavelength region is 400 nanometers to 2500 nanometers. And the pixel size can be varied. It can be brought down or increased to 5 meters by reducing the flying height, bringing the flying height lower. Then you have the HiMap. This is the hyperspectral mapper, which again is an airborne sensor with a variable in general with a spectral resolution where bands having from 100 to 200 bands with a bandwidth of 10 to 20 nanometers. The spatial resolution again depends on the flying height, which is varied from 2 to 10 nanometers. In general, it records between around 5 meters of the spatial resolution. Then you have the compact airborne imaging spectrometer, which was built by ITRS Research Limited of Canada. They provide data acquisition. This collected the data in 288 spectral bands ranging from 390 to 900 nanometers. It's a push-broom kind of a scanning with provides high spectral resolution with push-broom mode. It can collect data in 14-bit format for 288 spectral bands, and the spectral resolution can be varied to 2.5 nanometer intervals. However, the overall spectral range is limited to 650 nanometers, which is adjustable between 400 to 1050. Then we have other airborne sensors, which is HIDIS, which was developed by the US Navy, which has 10 spectral channels. The spectral resolution is 10 nanometers with wavelengths from again 413 to 2.5 micrometers. Its spatial dimensions of 320 pixels, and the spatial resolution again dependent on the altitude. Then another airborne instrument by the European agency is a digital airborne imaging spectrometer, which has 72 channels with a variable spectral resolution on depending on these different spectral regions. So 400 to 1200, the bandwidth is 15 to 30. Then in the middle infrared, you have 45 nanometer bandwidth, and then in the far infrared and in 2 to 25, it is around 20 nanometers. So the gap which is there in between coincides with the atmospheric absorption. In terms of satellite airborne remote sensing, in terms of satellite remote sensing or hyperspectral remote sensing, we have one instrument called moderate resolution imaging spectrometer. It is near hyperspectral. It's not exactly hyper, but to be considered to be a hyperspectral, which is a near polar whisk-broom scanner with 36 bands, 20 in the visible infrared, near infrared, the shortwave infrared band up to 3 micrometers, and then 16 bands in the thermal, and it has a variable spatial resolution of 250, 500 and 1 kilometer. So if you would like to have all 36 bands, then 1 kilometer spatial resolution is there to provide you data in all 36 bands. So it has a core spatial resolution, but it has large number of bands which are slightly contiguous in nature. Then we have this instrument on board the Hyperion, which is on board the NASA's Earth Observing Satellite, EO1, launched in 2000. It's a push-broom technology. It is in a platform which is at 705 kilometer sun-synchronous orbit, and it is 1 minute behind Landsat. It has the same spatial resolution as that of the Landsat, and this sensor detects 220 bands with 10 nanometer spectral resolution in the wavelength region from 400 to 2500 nanometers, and records in 12-bit radiometric resolution. So the 30-meter your spatial resolution is exactly matching to your Landsat's spatial resolution. However, the swath width is different. In case of Lancer, the swath is 185. In case of Hyperion, your swath is 7.5 kilometers wide, but the length of the image which is provided is 7.5 by 100 kilometers. Then, as I said, from the European Space Agency, you have this compact high-resolution imaging spectrometer, which is on board the Proba satellite, which provides you data with 18-meter spatial resolution, 200 spectral bands in the region from 400 to 2.5 micrometers, with 18 kilometer is the swath of the data. There's another satellite which is near enough to be a hyperspectral sensor is your MERIS, medium resolution imaging spectrometer, with a spatial resolution variable but around 300 nanometers, which has bands with variable spectral resolution in different parts of the spectra. You have ranging from 2.5 to 10 nanometers. And the spatial resolution is also variable across the spectra is 300 to 1200 meters. And the swath is a larger, because it's a core spatial resolution, the swath is larger, around 1150 kilometers. Then initially, India also launched another instrument which was on board IRS-P3, which is called Model Optical Scanner, which had 3 instruments, MOS A, MOS B, MOS C, which was primarily designed for ocean and atmospheric applications, where we had spectral channels designed with the spectral resolution required for atmospheric and ocean studies. So it had a radiometric resolution of 16 meters and spatial resolution around more than 700 meters, and again variable with different instrument, MOS A with around 2.5 kilometers, MOS B with around 7.2, and C as around 1 kilometer spatial resolution. But the bands chosen and the contiguity of the bands chosen was as per the application, like for atmospheric, aerosol and other studies, which the data, the processing and the output used from these can be used for atmospherically correcting the other broadband remote sensing data. But ISRO also made an initiative to launch the hyperspectral imager over the Indian mini satellite, which was launched in April 2008 with a spatial resolution of around 500 meters, and the number of spectral bands is 63 with a spectral resolution of 8 nanometers in the wavelength range from 0.4 to 9.5 micrometers, and the radiometric resolution was 11 bits. Then another instrument which India launched in the hyperspectral region is the onboard the Chandrayaan, which is which has again 64 channels after the success of the IMS in the visible near infrared range. Similar to that from 0.4 to 0.95 micrometers, with a spectral resolution of better than 15 nanometers, and the spatial resolution was improved from 500 to 80 meters with a swath coverage of 20 kilometers. Now, the potential of various applications of hyperspectral data, if you can summarize, is it can be utilized effectively in various fields of earth science. We can compare the difference between the existing multispectral satellite capabilities and hyperspectral. So, for example, in case of geological applications, presently the multispectral provides you the land cover classification, or can say geomorphological broad categorization. If you go for hyperspectral remote sensing data, you can go for precise mineral mapping and identification of various minerals on the ground. In terms of forest applications, at present, with the existing multispectral, maybe the land cover classification at various classification levels, but with hyperspectral, we can have species identification, vegetation stress studies, detailed stand mapping, foliar chemistry, and many more. With agriculture, again, land cover classification, limited crop mapping, but with hyperspectral, one can aim at soil mapping, crop differentiation, and crop stress studies, these to name a few. In environmental management areas, land use monitoring is possible with the existing satellite capabilities, whereas from hyperspectral remote sensing we can attempt to chemical mineral mapping and their analysis. So for the geological application, as I said, you have mineral targeting. For soils, high resolution imaging spectrometer holds for understanding the soil chemistry and its genetic and fertility classification. Vegetation, as I mentioned, the species identification, diversity, drought, disease, the stress in the vegetation is due to the moisture, nutrient, the plant transpiration rate, photosynthetic activity, all can be mapped using the imaging spectrometer data. In case of urban applications, if you have high spatial resolution urban datasets, hyperspectral datasets, we can identify different types of road surfaces, building material, roof material using hyperspectral data. So this is an example of, again, airborne imaging spectroradiometer, AVRS datasets, where different type of parking areas, parking lots where vehicles are placed, parking lots where it's empty of concrete and with tar material, all have been categorized. If you look, the profiles are different and they can be easily identified accordingly. In case of atmospheric studies, atmospheric parameters, clouds, environment, the climatology can be understood. Oceanography, the photosynthetic potential by detection of phytoplankton, detection of yellow substance. So probably in all these applications you have these lectures where they will demonstrate the case studies related to it. These are some of the examples which have been attempted at IRS, like to using hyperspectral remote sensing for studying the soil quality assessment. So if you look here, you can see on the right hand side the spectral signatures of different types of salt affected soils with varying levels of surface organic matter content, and the relationship between soil salinity indicators and soil organic and organic matter with the Hyperion data was established, and accordingly soil salinity indexes were determined, and then the soil organic content mapping was also attempted using the hyperspectral datasets. This is another example where a land cover mapping was done with hyperspectral data and was compared with the land cover mapping attempted with Landsat and with LE, which had better spectral resolution as the other multispectral bands, and whereby species level identification within the vegetation areas was possible with hyperspectral data. There's another example where the hyperspectral data was integrated with the microwave datasets for better discrimination of vegetation features. This is another example with the geological application at IRS, where mineral mapping was carried out for iron ore detection using the Hyperion data, and lithological mapping using in the Udaipur area using the Hyperion. So you can see the red areas, iron ore mines are there. So there is a separation of iron ore mines from the overburden dump material could easily be possible with the hyperspectral data. Overburden mines are the yellow areas in this. This is the same example, that the effect of mining on heavy metal concentrations in stream sediments using geochemistry analysis and hyperspectral remote sensing data sets. Now, hyperspectral remote sensing, since the data is of a different characteristics, the kind of processing required is also different from your multispectral remote sensing. So we can categorize into three categories: pre-processing, feature reduction, and classification. Pre-processing primarily includes your radiometric calibration, as I said, atmospheric correction and geometric correction is required. Now, the Hyperion sensor, this is an example of Hyperion sensor, but in general the hyperspectral datasets may have a few artifacts in terms of bad pixel, bad column correction, which needs to be corrected before further processing. Atmospheric correction is required to convert your the DM values into the spectral profiles, the ground reflectance profile, which then can be compared with the ground collected spectral response data sets, and then identification of those objects can be made possible. For atmospheric correction, we have different approaches. You have image-based correction methods, and which are relative in nature, and radiative transfer models, which provide you absolute correction. So probably in the subsequent lectures, more in-depth would be told to you on these approaches. In hyperspectral remote sensing, another thing which is very important is the spectral libraries. These are the basis which can be, these are the reflectance patterns which are used as a reference for identification of material using hyperspectral data sets. So spectral libraries are basically collections of spectra of different surface materials generated from laboratory and ground-based measurements. They contain spectra of individual species, and they are often grouped in the surface types like vegetation, soil, man-made material, and sometimes by grain size fractions. And they are acquired at different test sites representative of various terrain and climatic zones using the ground-based spectroradiometer. So this database enables identification of materials by matching their spectra with the spectra obtained from the Earth's surface. So in order to obtain a perfect matching of the ground-based spectra to the image-based spectra, atmospheric correction is required, so that the problems due to the atmospheric interferences are nullified by performing the atmospheric corrections. So publicly there are many spectral libraries which are available, which are also available in the NV software. They are there as astrospectral library on the internet, and one can create their own spectral library by taking the instrument and going to the ground and measuring it and generating these spectral libraries for their applications. There are various mapping techniques also. The mapping technique also slightly changes with hyperspectral data because you have large volume of data. Before mapping, you have also to do a feature reduction technique, feature selection technique, which is required, because since we have redundancy of information, some methods like PCA or other modern methods are also required to reduce the correlation between the bands and bring out the reduce the redundancy between the bands and bring out most discriminant or separable bands which can be utilized for identification of features. Then the mapping also similarly, the approach is slightly different from the multispectral. There are various techniques like spectral matching approaches, spectral feature analysis, and subpixel methods which are utilized in hyperspectral remote sensing, again which will be covered in subsequent lectures. So this is an example of spectral angle mapper where for different features these methods are utilized, and you can get the proportions of the land cover present in a particular image. For example, the white in this area shows all the grassland. The white tones in the second image on the upper side shows the urban area. Similarly, the forest and the SAM classifiers. The unmixing analysis, unmixing approaches, which is kind of a soft classification which creates 3 levels of images as per the this is more useful to overcome the mixed pixel problem. So within a pixel, whatever is the land use land cover fraction present, that proportions are highlighted in each of the fractions. So the first one is a soil fraction map, then water fraction map, and this is the vegetation fraction map, and the error in the analysis. Lastly, I would like to conclude the various software for hyperspectral data processing which are available. They are one is very common, probably your exercises would be on this, is the environment for visualizing images, that is NV. You have it on Easy Pace or what is called now Geomatica. Then LDAS Imagine Hyperspectral module. Then you have the Hyperspectral Imaging Processing Toolbox in MATLAB, and Multispec and PNT MIPS. So these are the few softwares which are there, which provides you with the capabilities of hyperspectral data processing. Thank you. If you have any questions, I'll be ready to answer. Questions from Harsak is one is then what is a spectral angle mapper? A spectral angle mapper is a technique for image classification which considers the angle between the reference spectra and the target the pixel to be classified. So it considers that angle for classification. This will be in depth covered to you in the classification techniques when it will be covered in the series of the lecture within this course itself. And another question is, what is the difference between thermal imaging and hyperspectral remote sensing? Thermal imaging is hyperspectral is basically acquisition of data in many narrow contiguous bands. If you're collecting, you can collect hyperspectral data sets in thermal region. Thermal region is the acquisition of the emitted radiation in the wavelength region from 3 micrometers to 14 micrometers. Whereas hyperspectral is, you can have, it's collecting information in large number of wavelength regions, or you can say with a narrow spectral, with a high spectral resolution, or you can say narrow bandwidth. So you can have hyperspectral data sets even in thermal region. In thermal region, you can collect the thermal radiations in narrow bandwidths and sampling it more. So like in MODIS, you have 16 wavelengths available, 16 bands available in the thermal remote sensing. So you can have hyperspectral measurements is basically collecting number of, having large number of observations. I hope I answered your question on this. And if there are no more questions, we'll stop it for today.